it's a small gap, and so this is this region of frequencies where the light you can get in your face when you put it in because of Bragg reflection. Okay? And that is that schematic of that transmission spectrum I showed you earlier. Now, the thing I'm interested in here, and one is interested in generally in slow light, is that, well, inside this band gap, the light you get back in your face. Okay? And in a sense, you can say that the group velocity there is zero. Far away from this Bragg frequency, well, this refractive index contrast is so small, it doesn't do anything. And therefore, the group velocity here and there is essentially CLN, the speed of light in vacuum divided by the refractive index. So if it's zero here and CLN there, then presumably it has to vary smoothly between there and there for these intermediate frequencies. And that is indeed what happens. So outside the band gap, you have this group velocity going from 0 to CLN on both sides. Now, typically, because again, this very small refractive index contrast, this here, it goes from 0 to CLN over a fraction of a nanometer. And therefore, the dispersion, which is the rate at which the group velocity varies with frequency, is extremely large, and it has an opposite sign on both sides of the photonic band gap. Right here it goes up with wavelength, here it goes down. If you work out the signs, you find that you have normal dispersion on the long wavelength side and anomalous dispersion on the short wavelength side. Okay? So, this grating does more than simply transmitting or reflecting light. It has this very strong dispersion associated with it. And of course it needs to have it because of this very strong dispersion, even though the transmission can be very high. Okay, so let's now look what you get out of a typical experiment here, right? Let's do an experiment, and we do it at the short wavelength side of the band gap. That's the same side I had on one of my first slides. There I looked at a function of frequency. Here I looked at a function of wavelength. And that's the problem with optics always, right? You can do it as a function of one or the other. You always get confused. It's the same side. It's the short wavelength side. And let us tune just inside a band gap, where the transmission is very low. And let's now see what happens. Well, intensity becomes high. You have this Kerr law again that I mentioned a minute ago. The band gap shifts as a result. This is the scenario I described to you early on. And so you expect the transmission to go up. And at these relatively low, well, these are still high intensities. Most materials are the nonlinearity is fairly weak. But in these relatively low intensities, I'll tell you later what they are, that is more or less what happens. But there is one additional feature which drives the whole thing. You have a structure here which is very dispersive, and it also has a nonlinear effect. Your intensity is high enough to get this nonlinear effect. And under quite general circumstances, you can show that when you have dispersion on nonlinearity, and the signs are appropriately chosen. What I mean by that is that if the nonlinearity is positive, which it happens to be in glass, then your dispersion needs to be anomalous. Then you get under these very general circumstances, soliton formation. Now what are solitons? They are pulses of light in which the nonlinearity balances the dispersion. So where a linear pulse broaden, because of the nonlinear effect, the high intensity soliton stays together. Okay? These are not subtle effects for which everything needs to be just right, which is nice. If you're kind of roughly in the neighborhood, the soliton will form itself, and any energy it doesn't need, it will shed. That's called radiation. And radiation essentially behaves linearly, and the soliton forms itself. So you don't have to try very hard to get one. You get it for free. Okay? Now associated, so you get this soliton formation here, and in addition to that, we're in a region where light travels very slowly, as per the earlier argument on the previous slide. And so you can have the possibility, at least in principle, to have these pulses that propagate very slowly, which is what you want, without broadening, because the very strong dispersion is in a sense balanced or cancelled by the nonlinear effect. Now let's see what happens. The experiment is schematically looks like this. We use a microchip YAG laser, emits pulses a couple of hundreds, well almost a nanosecond. We've used a couple of different lasers. They all have the same rough specs. The pulse that comes out has the shape of a shark fin, for reasons I don't understand, so you will see shark fin-like pulses in all my upcoming slides. That's the reason. It doesn't do anything profound. Then it goes into this fiber grating. Now, these YAG lasers are not tunable, so rather than tuning this and keeping that constant, what we do instead, we tune the grating and of necessity keep this constant. And we tune the fiber grating simply by stretching it, all right? Because when you stretch it, the period goes up, and when the period goes up, the break frequency shifts, right? So that's quite straightforward. And then it's measured by the standard kit on the other side. Okay, and this is the spectrum of one of the gratings that we did our experiments on, right? This is on the dB scale now. This is wavelength. These things at the edges really crash down. We can't measure how deep this goes. Just say, but it's certainly 40 dB. Yes.
If you have the fiber and you do the UV holography once, then the fiber keeps the reflected.
It's a permanent effect. Oh, sorry. I should have said that. Thank you. It is a permanent effect in that if you keep it at room temperature, it stays there for years. If you heat the fiber up a couple of 100 degrees, it goes away. Okay? It has to be permanent because at some point in the late 90s, fiber gratings were one of the standard tools, as I mentioned earlier, in the telecommunications industry. They used them to gain flattened erbium doped amplifiers. And